Uh, okay, let's start the session. Good evening, everyone. This is Saravanan, PhD scholar and Prime Minister Research Fellow of Department of Civil Engineering, National Institute of Technology, Tiruchirappalli. So I am a PMRF scholar. So as a part of PMRF deliverable, I have to take 2 weeks of session in NPTEL. So I'm a part of TA in Municipal Solid Waste Management course in NPTEL, which was originally taken by Dr. Ajay Kalamdad sir from IIT Guwahati. So all the presentations are from credits are to him only. So in this 2 hour session, first we are going to see in the first hour we are going to see about the same lecture material what sir has taught in the class, and in the second 1 hour we are going to discuss about the old assignment problems. Okay, so this is the 8th week of the session. So in the first week we have discussed about what is solid waste and the history of solid waste management, and what are the types of solid waste, and based on different source of generation. And 1 second. Sorry for the interruption. Sorry for the technical glitch. Okay, I will continue the session. So in the first week, we have discussed about what is solid waste and what are the types of solid waste. And then the second week, we have discussed about the characteristics and different properties of solid waste. And in the third week, we have discussed about the functional elements of solid waste. That is, first one is generation, second one is collection, third one is transfer and transport, and the fourth one is processing. Sorry, second one is storage and handling, third one is collection, fourth one is transfer and transport, fifth one is processing and transformation, and the sixth one is disposal. These are the 6 functional elements of solid waste management. And in the third week we have discussed about the storage and handling, and fourth week we have discussed about how to collect the solid waste, that is primary collection and the secondary collection. We have solved some of the problem related to stationary container system and the hauled container system in secondary collection system. And in the fifth week, we have discussed about different processing techniques like physical processing such as screening, magnetic separation and all, and then some sorting techniques in MRF, that is material recovery facilities. And we have also discussed about the waste to energy plants, like incineration, gasification and pyrolysis. In the seventh week we have discussed about the biological transformation, that is composting, and the different types of composting and vermicomposting and all we have discussed. And the eighth week we are going to discuss about the anaerobic process, that is anaerobic digestion process for the solid waste management. Okay, so let's move on to the course material. Yeah, so we are in the eighth week. So that is the biological transformation part two, that is anaerobic digestion. So in the last week we have discussed about the aerobic process, that is composting. In the composting also we have discussed about the different types like open and reactor type. In open type we have two things. One is windrow. Another one is static pile. Windrow is agitated pile. Static is static with the aerated pipes. In the reactor type, we have horizontal reactor, vertical reactor, and the batch reactor. Same thing, we are going to discuss about the anaerobic digestion. So this you have already known from your school days itself. Anaerobic digestion, like gobar gases from cow dung. People are making biogas, and they are using the gas to produce to generate cooking fuels and also to generate electricity. So this is the basic of anaerobic digestion, and how it works we are going to discuss. Okay. Yeah. So this is the fifth part of functional element of solid waste management, that is processing and transformation. The processing is physical and transformation is chemical treatment methods. Okay. So here we are going to discuss about the anaerobic digestion. So what is anaerobic digestion? It is a controlled process. So all the process what we are doing in the solid waste management is controlled process. That's what the difference between incineration and burning. Burning is uncontrolled firing, but incineration is a scientific controlled method. Similarly, dump site and landfill. Dump site is unscientific manner of disposal of solid waste, but landfill is scientific manner of containment of solid waste in a proper environment. Okay, like this we have unscientific and scientific manners. Like that also anaerobic digestion will happen in dump sites, but this anaerobic digestion is a controlled process in a sophisticated environment. So anaerobic digestion is a controlled process involving microbial decomposition of organic matter. So it is again a biological transformation system. So we are using microbes in composting also. It's not mechanical, it's a biological transformation. We are using microbes to degrade the organic material in the solid waste. Okay, similarly here also we are using the microbes to degrade the organic matter in the solid waste in the absence of oxygen. That's why it's called anaerobic digestion. Okay, so I hope you got this. Anaerobic digestion is in the absence of oxygen, but also the absence of electron acceptors like sulfates, nitrates and oxygen. So SO4 2 minus and NO3 also will have some oxygen embedded in it. So anaerobic digestion is taken place in the absence of any electron terminals, terminal electron acceptors like sulfates, nitrates and the oxygen. And AD consists of number of complex biochemical reaction. So we are going to discuss about the reaction in the upcoming slides. So what are the four major reaction that is going to happen in the anaerobic digester? So in that, microbes that survive in the oxygen-free environment, that is called anaerobes. Anaerobes are the microorganism which will survive only in the absence of oxygen. So during this biogas production, during this process, biogas will be produced. So that is the product we are going to get. So biogas is the composition of methane, carbon dioxide, hydrogen sulfide, hydrogen and the hydrogen. So major part will be methane. Methane is about 70% and 30% is carbon dioxide and some trace amount of H2S, N2 and H2. So the methane gas that's what we are going to get, that is having high calorific value. So we can use this as a fuel or to produce electricity. And then the leftover, that is called substrate, the sludge we will call, that is called digestrate, or the digestrate, which is rich in nutrient that can be used as a soil fertilizer or soil conditioner. So this digestrate in the wet mixture that can be separated into solid and liquid part. Okay, so this is the process diagram of anaerobic digester. So organic matter is fed into the digester. So major part is the digester. Digest is what we need. So in the digester we are feeding the organic matter and the biogas is produced by the anaerobic digestion process. And the final solid product is the digestrate and gaseous product is the biogas. So biogas we can use as a heat energy or as a source of heat energy, or you can use to produce electricity, and we can also use the gas in its original form as a gas grid, or as a fuel for cars like bio CNG and all. We can use this biogas. Okay, so biogas is a renewable energy source, so used as a fuel and also for the production of heat and electricity. um, so this anaerobic digestion process can be used for already this AD process is common in wastewater treatment. The same we are utilizing in the solid waste management process also. So in wastewater treatment, like industrial wastewater, which is having high strength of COD, like more organics are present, more recalcitrant organic are present, we can use this type of anaerobic digesters. Okay, which cannot be degraded by the aerobic system. We can use this anaerobic digesters. So some fact like Jan Bapta van Helmont in 17th century, he was the first who found this method, that is decaying organic matter resulting in a flammable gas. So first digestion plant was built in Bombay in India in 1859. Yeah. So this is the composition of biogas. As I mentioned, methane will constitute about 40 to 70% by volume. For around 65% it will be, and then carbon dioxide is around 30 to 60%. So it will be around 35. So 65, 35 will be the major composition, methane and carbon dioxide, and some other gases will be around 1 to 5% by volume. So which includes hydrogen, which is 0 to 1%, and hydrogen sulfide 0 to 3%, and some part of nitrogen also. So this is because if it is aerobic digestion, we will get CO2 and heat and water vapor, that is CO2, H2O and water vapor, heat. But here it is anaerobic digestion. So major product what we are getting is methane, so CH4, and then some part of CO2. Okay, when this biogas is not useful for energy production, whenever the carbon dioxide is exceeding the amount of methane in the biogas, then it cannot be used as a fuel. So no flames will come, and which is of no use. So whenever the carbon dioxide is rising, that section is called the feeding part. So you can see here the methane is around 60% and the carbon dioxide is around 20%. So whenever there is a new feed is coming, so this carbon dioxide level will increase and the methane level will decrease, because we are introducing some aerobic condition. Like that it is going on. Whenever the methane is reducing and carbon dioxide increasing, whenever the carbon dioxide reaches a level of 44%, then the biogas cannot be used to produce flame. So that is of no use. So 44% is the limit for carbon dioxide. So 35 is the optimum level, 65 is the optimum level for methane production, methane composition. Then what are the stages of anaerobic digestion? As I mentioned, many complex biological reactions are taking place in the anaerobic digestion process. So out of which four major stages. One is hydrolysis, acetogenesis and methanogenesis. Please remind this is very important. Hydrolysis, acidogenesis, acetogenesis and methanogenesis. Okay, so whatever the organic feed we are giving, that is called the substrate, which is of complex in nature, complex organic matter. So this we are first hydrolyzing. Hydrolyzing is addition of water. Why we are adding water? To break down the complex organic matter into simpler. So to break down the complex organic matter into simpler sugar molecules, that is called simpler glucose molecule, that is called hydrolysis. So here hydrolytic bacteria will play its role. Using some extracellular enzymes, it will break down the complex organic matter. After this simpler form, which is whatever the complex organic matter like protein, fat and carbohydrates are converted into peptides and kind of simpler organic matter. That simpler organic matter, that is the monomer, is converted into volatile fatty acids, that is called acidogenesis process. Acid formers are the bacteria which will be involved in this process, that is called acidogenesis. Simple monomers are converted into volatile fatty acids. So here what are the microbes that is playing its role? Fermentive acidogenic bacteria. Then after forming volatile fatty acids, this volatile fatty acids are converted into acetic acid, that is called acetogenesis. So all the acids are converted into acetic acids. Acids are break down into acetic acid, that is called acetogenic bacteria that will play in its role. And then finally from the acetic acid the methane will be produced. So there are two pathways. One is from the acetic acid, or from directly from H2 plus CO2 will also form CH4. So that this process is called methanogenesis. Methane formers or methanogenic bacteria will play its role. So methane produced from acetate or H2 and CO2 it will form. Okay, these are the four major reactions that is going to happen in the anaerobic digestion process. So the complex organic matter is first converted into simple monomers, that is called hydrolysis, and the simple monomers are converted into volatile fatty acids, that is called acidogenesis, that is the acid forming stage, and then the volatile fatty acids are converted into acetic acid, that is called acetogenesis, and then from the acetic acid and H2 plus CO2, the methane will be formed, that is called methanogenesis. Finally, methane will be produced, that is called biogas. Microorganism involved in each stage is mentioned in this gray color. First one is hydrolytic bacteria, second one is acidogenic bacteria, and methanogenic bacteria. Okay. So here the biomass will be converted into H2CO2 and acetic acid as I mentioned, or into simpler compound into acid formers. Then acid will be converted into acetic acid, and then biogas will be produced. So like this, different pathways will be there. So first, these are all acidogenic bacteria which will directly convert into acids, and then from the different acids, acetic acid will be formed. That is acetogenesis. From acid and from acetic acid and H2CO2, this methane will be formed, that is methanogenic bacteria. So the color code you can see, this is the different types of bacteria also mentioned in the photographs. Yeah. So how the COD is getting balanced? 90% of the organics are converted into biogas. Only 10% will remain as sludge. So this is the major advantage of anaerobic digestion process. Lead sludge is formed, but in aerobic digestion process like ASP, in water treatment I am talking about, some of the ASP process or many aerobic process will produce large amount of sludge. So in anaerobic digestion process, the sludge production will be less, and the time taken for the reaction will also be lower. So this is the advantage of anaerobic process. So COD 90% will be converted into biogas and 10% will be converted into sludge. That is good in nutrition value, so that can be used as a soil conditioner or as a fertilizer. Okay, now we are going to discuss about each stage in detail. So hydrolysis process, insoluble complex organic material like protein, polysaccharides and fats are converted into soluble monomers, that is the simpler compounds. So protein will be converted into peptides, polysaccharides will be converted into fatty acids, fats are converted into saccharides. So these are the complex organic matters and the simple monomers, proteins, polysaccharides and fat into peptides, fatty acids and saccharides. So this is a slow process. In the whole anaerobic digestion process, the rate limiting step is the hydrolysis. What is rate limiting step? Rate limiting step is the one which will take the longer time in the whole process. So if the whole anaerobic digestion will take 2 hours, means hydrolysis alone will take 1.5 hours. So for example, I am saying, so that is called a rate limiting step. So in the 4 stages, hydrolysis is the rate limiting step. Okay, so it is a slow process. This stage is the rate limiting stage. The biological, so whatever the reaction involved is the complex organic matter that is added with water, that is called hydrolysis. After hydrolysis, it will be converted into simple monomer C6H12O6. Everything will be converted into simple glucose or sugars. Okay. In acidogenesis, the simple glucose will be, yeah. In acidogenic phase, the simple glucose will be converted into acetic acid, that is CH3COOH. Okay, so or any type of acids it will form, that is called the acid formers, acidogenesis phase. So the hydrolyzed products are converted into simple molecules with a low molecular weight, such as fatty acids. Like one of the fatty acid is acetic acid. Some other are called propionic acid, butyric acid. Some of the isovalvulic acids are also will be produced from this acid formers. So the simple monomers are converted into volatile fatty acids. So at this phase, acids are forming. That's why the pH of the whole system will be reducing to 4. So affected by a diverse group of bacteria, which is capable of bringing down the pH inside the digester to 4 also. So at this stage, the pH will reduce to 4, but the methanogenic bacteria, that is the methane formers, will not work at this pH, acidic pH of 4. So to increase the pH, we have to add alkalinity additionally from as an external source, or the whole system will automatically have a buffering capacity which will adjust the pH so that the methanogenic bacteria will work and convert the things into methane. Okay, so at this phase the pH will be very low to around 4 also. Then acidogenic base phase. In this stage, all the other acids will be converted into acetic acid, or some of the CO2 and H2O will also be converted into acetic acid. Okay, so in this phase, the product of acidogenic stage, that is organic acids, are converted into acetate, that is acetic acid plus H2O and CO2 by acetogenic bacteria. So this will be having two group of acetogenic bacteria. One will convert H2, one will control proton reducing acetogenic bacteria or H2 forming bacteria, which will generating acetate, CO2 and H2O. Others will be homoacetate that catalyzes the acetic acid conversion to CO2 and H2O. So these are the two forms we are going to get. One is hydrogen and CO2 it will be producing, another one is producing acetic acid. So again methane will be produced from both the stages only. That is called methanogenesis. So methanogenesis also have two pathways. One is acetic acid to CH4 and CO2. Another one is CO2 and H2 will form H2O will form CH4 and H2. Here O will not form. Okay. So this phase will work only in the neutral pH. But acidogenic bacteria will form will reduce the pH to even around 4. So we have to increase the pH, or the whole system will have a buffering capacity to increase the pH to neutral, in around neutral, so that the methanogenic bacteria will play its role. So these methanogens are methane formers from the final product to final product of acetogenesis from some of the intermediate products. 1 second. Okay. So we have discussed about the 4 stages of anaerobic digestion process, that is hydrolysis, acetogenesis and methanogenesis. So finally the product is biogas that will contain a major amount of methane, that is around 65%, and a little quantity of CO2, that is 35%, and some trace element of hydrogen, nitrogen and H2S gases. What are the factors that is affecting the anaerobic digestion process? So various factors such as temperature, pH, volatile fatty acid presence, and a Seabain ratio. These are the factors which will affect the anaerobic digestion process. So we will look into one by one. First one is temperature. One second. Yeah. So temperature we can divide into 3 stages. One is psychrophilic temperatures, and then mesophiles, and then thermophiles. These are the 3 temperature range in which the microorganism will grow. Psychrophile will be less than 20 degrees Celsius, and the mesophile bacteria will grow in 20 to 45 degrees Celsius, and thermophiles are 45 to 65 degrees Celsius. So the growth of methanogens will be higher. Methanogens are the methane forming bacteria. So the methane producers will grow as a maximum at thermophilic temperature only. So this temperature has a major role in methane production, that is the yield. So anaerobic digestion is mainly majorly okay. So anaerobic digestion is depends majorly on this temperatures. Okay, so at thermophilic temperature, the methanogens will grow at a maximum rate of around 100% also. Okay. So at the thermophilic stage, what are the advantage and what are the negative effects it will cause to this anaerobic digestion process? So at thermophilic temperature range, it will increase the hydrolyzed soluble product. So at the first stage itself, it will form a good monomers from the complex organic matter. It will form hydrolyzed soluble product and increase the reaction kinetics. So it will shorten the reaction time, and the HRT will also be lower, so that we can give a large feed to the system, so that the HRT will be lower and improves the physicochemical properties of the soluble substrate. But the negative effects of this thermophilic temperature are it will increase the fraction of free ammonia. So the free ammonia will form a lot, So ammonia is the inhibitor for the microbial growth. So the large amount of ammonia production is not good for microbial growth. So it will affect again the yield of anaerobic digester, and the reaction stability will also be reduced, and high accumulation of volatile fatty acids at thermophilic phase. Large acidogens will be formed and the monomers are converted into volatile fatty acids, but the methanogens won't work. So a large amount of volatile fatty acid will be accumulated, which will reduce the pH even more, less than 4. So and then effluent quality reduces and toxicity increases of certain types of substrate. But if you are following the mesophilic temperature, the advantages are greater process stability and better richness in the anaerobic bacteria. But disadvantages are it will provide lesser biogas yield. So that is a disadvantage. So what we can do, we can follow thermophilic range for hydrolysis and acidogenesis, and then for acetogenesis and methanogenesis we can follow mesophilic phase. So that is the two things we can two stages of reactor we can design. In the first reactor we can maintain the thermophilic range temperature range. In the second reactor we can maintain the mesophilic temperature range, so that the hydrolysis and acidogenesis phase will occur in the first reactor, and then acetogenesis and methanogenesis will take part in the second reactor at a mesophilic temperature range. So too high temperature will cause metabolic rate to decline. That's what we have to maintain an optimum temperature for the bacterial growth in the anaerobic digester. Then the second factor affecting the anaerobic digester is pH. So as I mentioned, volatile fatty acid accumulation will reduce the pH. So methanogens are effective only in the neutral pH of around 6.5 to 7.5. But at acetogenic genesis phase, the pH will drop to even 4. So how to maintain a neutral pH? The pH vary due to the parameters such as volatile fatty acid, bicarbonate concentration, and alkalinity. So we have to balance VFA and alkalinity so that the pH will be maintained at a neutral, and the methane production will be higher. To maintain the constant pH level, the relationship between the volatile fatty acid and the bicarbonate, that is the alkalinity, we have to maintain so that the buffering capacity will be maintained. Okay, so one of the risks for digester failure is excessive accumulation of volatile fatty acid, as I mentioned. So if the temperature is higher, acidogenesis will play a larger role, and volatile fatty acid will be accumulated, and then it will lower the pH to around 5, inhibit the growth of methanogens. If the pH is very high, that is alkalinity is more, means it will prove the toxic. It will prove to be toxic to most anaerobes. So it will again inhibit the biological function. So we need a neutral pH of around 6.5 to 7.5. Okay, so here is the graph which shows the activity of the microbe at a different pH range. So you can see the methanogens are really active, that is around 1. That is the highest activity we can get at the pH range of around 7 to 8. So that is the neutral pH range. So optimum pH range for anaerobic digester is 6.8 to 7.2 for the methanogenic bacteria. Okay. So two main operational methods. One is to correcting an unbalanced low pH range. Hello, am I audible? Hello, am I audible? Hello, hello. Hello, am I audible? Hello.
Yes, sir, you're audible.
Sorry for the technical glitch. Yeah, I'll reconnect. I'll share.
Yes, sir.
Thank you so much. Yeah, hope the screen is visible. I'll continue. So we are discussing about the anaerobic digestion process and the four stages of anaerobic digestion, that is hydrolysis, acetogenesis, and methanogenesis. Now we are discussing about the factors affecting the anaerobic digestion. So the first one is temperature we have discussed, and the second one is pH. So the pH will be lower at the acetogenic phase because acids are formed. So in the hydrolysis phase, complex organic matter are converted into monomers, and in the monomers are converted into volatile fatty acid in the acetogenesis phase, and the volatile fatty acids are converted into acetic acid in the acetogenesis phase, and the acetic acid is converted into methane in the methanogenesis phase. So when the acids are formed, when the volatile acids are formed, that is VFAs, at the acetogenesis phase, the pH will drop to 4. So we have to maintain a proper buffering capacity so that the methane will be produced, because methanogenesis requires a neutral pH. So how to correct the low pH condition? We have to stop the feed so that whenever the pH was reduced very lower than 4, then we have to stop the feed so that the volatile acid production will be stopped. Then the pH will automatically become neutral to around 6.8. Then the second method is addition of chemicals, external chemicals, to raise the pH. So like alkalinity, bicarbonates, carbonates, and hydroxides we can add so that the pH will become neutral. Okay, so this is the methods for correcting the pH in the anaerobic digestion. This is the buffering capacity, that is the alkalinity. So the anaerobic digestion is itself having its own buffering capacity. What is buffer? Buffer is the condition to maintain the pH at a constant level without changing. The pH at 7 it will maintain, or some buffer will maintain the pH of around 12. So the anaerobic digestion itself having its own buffering capacity. Again pH drop. So it will produce some alkalinity, like ammonia will be converted, and then some salts of fatty acids will also be producing alkalinity, and some sulfates and sulfide will be reduced so that there is a alkalinity production, that is bicarbonates will be produced. Here the sodium acetate will be converted into sodium bicarbonate, and here acetate will be converted into bicarbonate. So this type of alkalinity production will stop the change in the pH drop. Okay, that's the own buffering capacity of anaerobic digester. So this alkalinity present within the system neutralizes the acid and prevents further pH drop. So external addition, if it is not present, then we have to add some external alkalinity to the system. Then the third factor which is affecting the anaerobic digestion is the carbon to nitrogen ratio. Whenever the carbon to nitrogen ratio is maintained at 20 to 35, that is the optimum range, so that will be suitable for the greater yield of methane. So our aim is to produce methane from the substrate, that is the solid waste. So whenever the methane production is higher, the system will work good. So the optimum CVN ratio of 20 to 35 will be maintained so that the production will be higher. Whenever the nitrogen is lower, that longer duration will be required for the digestion. Whenever the nitrogen is higher, too much production of ammonia, that will inhibit the microbial growth. So carbon serves as a source of energy to the microorganism, and nitrogen serves as a nitrogen controls the microbial population. So this two needs to be balanced. As I mentioned, the carbon to nitrogen ratio will to digest one part of carbon, the microbe requires 30 parts of nitrogen. So if there is a 1 mole of carbon, then 1 mole of nitrogen will be 30 mole of carbon, 1 mole of nitrogen will be required for the assimilation of the microbial for the microbes. So carbon is the energy source, nitrogen is the metabolic source, that is for its reproduction and growth. Then the organic loading rate, it's not leading, it's a loading rate. So organic loading rate, that is OLR, how much amount of feed we are giving into the anaerobic digester, how much amount of solid waste we are giving. So
So amount of volatile matter that is fed into the anaerobic reactor. So when the OLR is higher, then it will inhibit the microbial growth. Why? Because whenever we are adding more substrate, it will produce more volatile fatty acids. If the OLR is lower, what will happen? It will underutilization of microorganisms. That is called starvation. So we have two conditions in the digester. One is fast, one is feast. So fast is like what we will call in Vradam we will tell now, that is called fasting. Feast is like we are going for a hotel and we are eating anything, that is called a feast. So like this microorganism will have two conditions. One is fasting condition, another one is feasting condition. When the microbes are higher, but the food is very low, then every microorganism will fight for the food. That is called a fasting condition. The food is very high and the microorganism growth is very low. Then there is a feast condition. Many food is available. Like that, when the OLR's organic loading rate is very low, then more microbes are there, but very less utilization of the microbes to eat the food. That is called the underutilization of microorganism, leading to very slow rate of anaerobic digestion. So we should not provide high OLR and we should not provide low OLR. So it should be maintained at the optimum level. So optimized, it will be optimized based on the type of feedstock and the reactor temperature. The reactor temperature is higher, we can give more OLR. That is the condition. Then HRT. HRT is the hydraulic retention time. Average time the organic substance remains in the digester. So whenever we are giving a feed, how much time it is there inside the reactor before it is coming out from the outlet. That is the time, hydraulic retention time. So this will be followed in wastewater treatment also. The same terminology we are following in the solid waste treatment also. So the HRT affects the biological and chemical properties of the organic matter. So if the HRT is shorter, we require high temperature, like thermophilic bacteria will play its role, so that the HRT will be lower and OLR will be higher. Then volatile fatty acids. As I mentioned, whenever volatile fatty acids are more, the acid forming bacteria are more, then the pH will be lower and then it suppresses the methanogens. Methane production will also be lower. If we want more methane production, we have to maintain the neutral pH. So during the acidogenesis phase, two volatile fatty acids, namely acetic acid and butyric acid, which will be formed, which are also known to favor the methane formation. But at the same time, pH will also be reduced. So acetic acid contributes to 70% of the methane production. Other volatile fatty acids are like propionic acid, isobutyric and isovaleric acid also contribute around 30% for the methane production. So VF is higher, but it is good indicator and to monitor the performance of the AD. So VFA should be more, but again the neutral capacity will also be higher, so that the methane formation will also be higher. Okay, so this is the relationship between the volatile fatty acid and alkalinity I am talking about. So volatile fatty acid will be 200 milligram per liter, for example, and then alkalinity is 2000 milligram per liter, so that the pH will be maintained at 7. So you can see in the next graph, volatile fatty acid is 200, alkalinity is 2000. In the same case, the pH will be around 6.8 to 7, neutral pH only. Okay, when in case we are taking three cases. In first case, the volatile fatty acid start increasing, so high accumulation of volatile fatty acid. Still the pH is 6.8 only. So there is no change in the pH. That is the buffering capacity. We have high alkalinity, so that the buffering capacity is fine. And still the VFE is higher and the alkalinity is starting reducing. Still the pH is maintained at 6.8. So again we are having a at case B also, increasing volatile fatty acids and decreasing alkalinity, pH still remains stable. But even if it is volatile fatty acids have become very higher and then alkalinity become very lower, then only the pH start dropping. Then the natural buffering capacity become insufficient, so that the pH of the reactor starts to fall. So we can also maintain A condition or B condition, but not the C condition, so that the pH will drop. Then drop from neutral, then the methanogenic bacteria will not perform its role. So methane production will be lower. So this is the relationship between volatile fatty acid and alkalinity. So that the system having its own buffering capacity. Okay. So here the three condition you can see about the methane production. So at A condition also the methane production will be okay. At the B condition also the methane production will be okay, because the pH is similar to A 6.8. But in the third condition, whenever the volatile fatty acid started higher, and the methane production will be lower and CO2 will become higher. So in a general biogas, 65% methane and 35% CO2. Whenever the CO2 start increasing above 44, the biogas will not be flammable. There is no use of biogas. No need to. We can't use that as a fuel for cooking. We can't generate electricity from the biogas. So at the case C, methane production ceases. This changes and all because of feed. Whenever we are feeding extra organic load or solid waste, then the CO2 will start rising and again it will be neutralized. Okay. So here we are going to discuss about pre-treatment. What is called a pre-treatment and what is called a co-digestion. So as I mentioned, hydrolysis is the rate limiting step. So what is called rate limiting step? If anaerobic digestion takes 2 hours, hydrolysis, acetogenesis and methanogenesis, in the 4 stages, which stage takes more time? That is called the rate limiting step. The whole 2-hour process, hydrolysis alone will take 1.5 hours. Then it is called, as example I am saying, then it is called hydrolysis rate limiting step. So in the whole 4 classes, hydrolysis is the rate limiting step because it's having high increases the HRT. The whole process will be delayed. So we need a pre-treatment so that we can reduce the time required for hydrolysis. Why hydrolysis is taking place? To reduce convert the complex organic matter into simpler organic molecules, simple glucose molecules. So how to enhance this process? How to reduce the time required for hydrolysis? That is called a pre-treatment. How to do? So pre-treatment is a process of initiating or improving the efficiency of microbial attack. So how to do this? How to enhance the microbial attack process? That's what we are going to see in a 3 methods. One is called a physical, chemical, and biological methods we can use for pre-treatment. So the compact structure of biomass is disrupted into simpler molecules. So in pre-treatment we have 3 stages. One is biomass destruction will happen, improved solubilization will happen, so then microbial attack will also get increased and the biogas yield will be higher. Okay, so whenever it's simple like whenever you are eating a puri and instead of eating an idli, so idli will be digested easier, puri will take a large time to digest. So whenever we are mixing the puri with some curry, then it is easy to digest. So this is the simple process of pre-treatment so that it can be easy to digest. So that's for easy digestion of the microbes. We are giving some pre-treatment methods. So how to do pre-treatment by physical methods and biological and chemical method we are going to see in the upcoming slide. So why we need to do pre-treatment? So the readily biodegradable and soluble organic matter is not available. Whenever the whatever the present is highly recalcitrant to degrade. Recalcitrant means it will retard the degradation process. So at that stage we need to do pre-treatment and the rate of hydrolysis is conventional anaerobic digestion is lower, resulting in higher HRT. So to reduce the rate of hydrolysis, sorry, to increase the rate of hydrolysis we are doing pre-treatment because lower hydrolysis will take higher HRT. That is not good for the treatment process. So we need to lower the HRT. For that we need to increase the rate of hydrolysis. And then lower biogas yield if happens, we need to do pre-treatment to increase the biogas yield. Okay, so the substrates like maize, wheat, barley, which are all having lignocellulose substrate. So there are 4 types of organic compound. One is called sugar or glucose, cellulose, hemicellulose, and lignin. So the last 2 are very difficult to degrade. If sugar and cellulose are present, it is easy to degrade. But hemicellulose and lignin are present, that is very complex to degrade. So whenever the lignin and hemicellulose is present, we have to disintegrate the particle so that it is easier to degrade. Like these are the things like rice straw, barley straw, banana stems, and then energy crops like sunflower crops, and then some of the terrestrial and aquatic weeds like hyacinth plants and this type of plants will we need to do, and other organic waste like food waste and kitchen waste, which have lignin content, we need to do pre-treatment. So effect of pre-treatment on lignocellulose substrate. As I mentioned, see the whole complex organic matter structure. The outer red color is called lignin, and then the green color is called cellulose, and then the yellow one is hemicellulose. So if this type of complex organic matter is present, it is difficult to degrade. We need to do pre-treatment so that the lignin will be break down and then hemicellulose will be disintegrated and then the cellulose compound is easy to digest. that's called a liquid hydrolysate, and then solid residue will be separated. Can be easy to degrade. So this type of lignocellulose is present. We need to do pre-treatment so that it will be disintegrated. So diverse composition of complex structure which is resistant to disintegrate, we need to do pre-treatment. Then the cellulose and hemicellulose are polysaccharides that are being hydrolyzed into simple sugars. Lignin supports the cell structure. As you can see here, it is a support. It's supporting the cell structure, which is hindering the microbial attack. So we need to break the lignin layer by pre-treatment so that it will decrease the crystallinity of the cellulose. So when it's having a crystalline structure, it will be break down into uneven structure, which is easy to degrade. Okay. Then the food waste are having low biogas yield due to the presence of inhibitors and necessary break. Then the sludge biomass. Whenever we are having sludge like industrial sludge, municipal solid waste management treatment sludge, and then animal manure like cow dung, horse dung, cattle, any cattle dung, and then sludge from the food processing plant, we need to do pre-treatment. So this sludge will have extracellular polymeric substrates, which are very difficult to degrade. Again, it's a complex. So we need to do deflocculation, and then we need to get out the cell, that is called cell lysis. Then it's easy to degrade. Sludge biomass will have high organic content, and then the secondary wastewater sludge which has numeric microbial cells. Because whatever the sludge we are getting from the activated sludge process or any secondary tank, which have huge population of microbes. So this microbial cells, which is having outer cell wall, which is difficult to degrade. So that it's again an organic compound, but it's difficult to degrade. So this wall need to be digested so that disintegrated so that it can be easily digested by the microorganism present in the anaerobic digester. So this extracellular polymeric substances are called EPS, extracellular polymeric substance, which have a binding mechanism of EPS to cations. So this digestibility of the activated sludge need to be done in pre-treatment. So the COD reduction will be 30 to 35% in conventional anaerobic sludge treatment method. Very important. 30 to 35% of COD reduction will happen in conventional anaerobic sludge treatment methods. So another process like another complex structure is microalgae. As you know, microalgae are having cell wall, which is also again complex to degrade. So which will produce again algae are the plant which will produce use sunlight and carbon dioxide to produce its energy, so that the microorganism biomass supported by the higher photosynthetic efficiency, higher biomass yield, and higher CO2 fixation than higher plants. So the biogas production will be higher from this type of algae, but we need to do pre-treatment like crude glycerol, microalgae, which need to be pre-treated so that the biogas yield will be higher. Like macroalgal biomass also we need to do, because the rigid algal cell wall need to be disintegrated, like cell wall collapse after pre-treatment, so that the organic matter, simple organic matter will come out, can be easily digested. How to do pre-treatment? So mechanical pre-treatment will reduce the particle size. That is called a physical method. Physical and mechanical method, which will reduce the particle size, like shredding or segregation and shredding will reduce the particle size to around 1 to 2 mm, which is effective for hydrolysis. As I mentioned, if you are eating chapati, a bigger piece, it is very hectic to degrade. If you are shredding into smaller pieces and if you are eating, it is easy to degrade. So like that, particle size reduction will be required, and which will increase the surface area, which will enhance the enzymatic degradation so that it can be easily digested. And then different mechanical methods like knife mills and shredders, hammer mills, and ultrasonic treatment also can be used for size reduction. Okay, like these are the images you can see about the shredder. Some of the shredder used for in the industrial scale for shredding the complex organic matter. Then thermal pre-treatment. Thermal pre-treatment is again a physical method only. We are increasing the temperature to disintegrate the materials, substrate. Substrate is heated to around 125 to 90 degrees Celsius, so that for using some autoclave, hot air oven or microwave oven or hot water bath, we are but it requires an additional water before thermal pre-treatment. Otherwise, it will become the whole water will get evaporated and it will become dry in nature. It will stick to the equipment. So we need additional water before thermal pretreatment method. This is the important point. And then the disruption of hydrogen bond will happen in the lignocellulosic compounds. Some of the hydrogen bond will get disrupted, which will cause the biomass to swell. So that the pretreatment is success. This can be used as a substrate for anaerobic digestion. This thermal pretreatment is effective only in this temperature range of around 125 to 190. If the temperature is higher, like above 200, some of the recalcitrant soluble organic will form. So it again toxic to the system. So we need to maintain a temperature of around 170 to 190 degrees Celsius. If you are going above 200, some recalcitrant soluble organic will form. So that is not good for the treatment. Okay. So optimum temperature for waste activated sludge is 175, and for some of the crops it is 190 degrees Celsius. This is enough for thermal pretreatment. But this thermal pretreatment will add energy requirement to the system. So the normal anaerobic digestion process not require any energy, but the pretreatment technology like thermal treatment requires some energy, huge energy. So this will add cost and the environmental footprint of the treatment process. Then chemical pretreatment. Now we have discussed about the physical treatment, that is mechanical and thermal. Now we are going to discuss about the chemical pretreatment. How to do chemical pretreatment by acids and alkalis and some of the oxidant we can use. So if you are using alkali like lime, sodium hydroxide and calcium hydroxide, it will swell the lignocellulose compound. Whenever the lignocellulose compound is swelled, the lignin will be disrupted and it will be partially solubilized. So it can be easily digested. Then acid pretreatment, like some of the acid we can use, which will not disrupt the lignin, but it will break down the hemicellulose and disrupt the ether bonds. Then oxidative pretreatment like hydrogen peroxide and ozone will be used, but the disadvantage is too much oxygen will increase the proportion of CO2. Because anaerobic process, we know no need of oxygen. It is a microbial degradation process of organic matter in the solid phase in the absence of oxygen. So whenever we are doing some pretreatment with the oxygen, it will increase the proportion of CO2, not the methane. Okay. Then biological pretreatment method. This is good out of other three treatment method, because we are using microbes for the pretreatment. Again, we are using the pretreated substrate in the microbial digestion process only. So this is good for anaerobic digestion. Biological pretreatment involves using microbial agent like bacteria, fungi, and the enzymes, which will transfer the simple end product due to action of various enzymes, which will solubilize the organic matter. Like it will also increase the biomass yield of around 30%. But biological pretreatment is very slow process compared to thermal and chemical pretreatment method. Direct microorganism will be So direct microorganism will be added as a uh, substrate, and it will produce some enzyme which will solubilize the organic compounds. So this will be less energy intensive pretreatment, but it will take more time more time for pretreatment, and highly selective, no inhibitory byproduct will be formed. It's another advantage. But the disadvantages is the complexity and the cost. Again, it will be divided into anaerobic and aerobic, fungal and enzymatic addition. Then we are going to discuss about the co-digestion. Co-digestion is the process of adding two substrates into the anaerobic digester instead of monodigestion. Monodigestion is the process of giving one substrate to the anaerobic digestion system. But if you are mixing two substrates like sewage sludge and the food waste, and then industrial sludge and the kitchen waste, if you are cow dung we are adding, then this is called a co-digestion. Why we need to do co-digestion? What is called anaerobic co-digestion? And code is the anaerobic co-digestion. This is the simultaneous anaerobic digestion of homogeneous mixture of two or more substrates. Why we need to do co-digestion? Because some substrate will be having good carbon content, some substrate will have good nitrogen content. But for a proper anaerobic digestion, for a proper optimal condition, we need a C by N ratio of 25 to 30. So to attain a proper C by N ratio, we are mixing two substrate. That is called anaerobic co-digestion. So it will increase the biogas production and methane yield. So positive synergism. Positive synergism in the sense it will the metabolic activity will be synergized, and then the optimal attainment of lacking nutrients. One will have higher nutrient, one will have lesser nutrient, so if you mix both it will have an optimum nutrient level. And then the high CBN ratio, whenever the substrate is having high CBN ratio like mono digestion has poor processability, and then addition of rich nitrogen rich core substrate at the optimum ratio enhances the biomass degradation. This is the two important methods to increase the C and to increase the N value. So co-digestion will enhance the biogas production of around 25 to 400%. So in normal conventional anaerobic digestion, if we are producing 100 kilowatt of energy, then in co-digestion we can generate about 400% higher energy than the normal conventional anaerobic digestion. That is called monodigestion process. So the benefits are it's diluting the toxic substances. Some are having hazardous waste, some are food waste. So if we mix both, we are diluting the hazardous toxic substances. Then the nutrients will be balanced. The C and N got balanced. And then synergic effects of microorganisms. Some will have anaerobic, some will have anaerobes, some will have algae, some will have like this type of different bacteria and algae. Synergic symbiosis we can get. And then economic benefits and increasing OLR, higher methane yield. But the drawbacks are increased digested effluent COD. So our attainment is what are the substrate final digest rate we are getting should have lower COD value. But this type of co-digestion will produce a digest rate of having higher COD value, and then increase the mixing requirement. So if we are having two substrate, we need to do homogenization. For that, we need a proper mixing mechanism so that it will be mixed into a single compound before feeding into the anaerobic digestion. And then economically critical and additional pre-treatment is required. So again, it will follow the same four path: hydrolysis, acetogenesis, and methanogenesis. This will also form the same path, and then finally, the production of methane will be higher. The factors affecting the anaerobic digestion process. So the chemical composition, which is the major thing that will affect the anaerobic digestion, like carbohydrate rich compounds. If the carbohydrate is higher, then carbon will be more, then the volatile fatty acid production will also be rapid. When the acid production is higher, pH will drop. pH if it is dropped, then methane production will be lower, suppression of methanogenesis. So this is the subsequent problems associated with the carbon source. The carbon is higher, volatile fatty acid production will be higher, pH will be reduced, methane production will be lower. So suppression of methanogenesis. So what is the solution we can do? For balanced operation, high amount of simpler carbohydrate with lower content of easily degradable organic compound is recommended. So if it is easily biodegradable, then only the volatile fatty acid will be higher. So if you are adding some simpler carbohydrate which is having lower content of easily biodegradable material, then it is easy to suppress the volatile fatty acid accumulation. If it is rich in protein, whenever the substrate is rich in protein, then protein will be converted into amino acid. Amino acid will release ammonia ions. Ammonia ions again inhibit the microorganism growth. Again, it is a problem. So protein will also be adjusted with a suitable C/N ratio. If protein is higher, ammonia acid will be ammonium ions will be produced. Ammonia will be in higher concentration. It will inhibit the methanogenesis. If it is fat rich compounds, again fat will block and absorb the biomass. So long chain fatty acid will be formed. Complex high concentration of long chain fatty acid will inhibit the activity of anaerobic microorganism. Again here we need to mix the carbohydrate rich with the fat rich material. Again we are balancing the C/N ratio. Carbohydrate rich material with the fat rich materials will be the nutrition balance. Okay. The first factor is chemical composition, which will affect the co-digestion process. Second one is the temperature. So as I mentioned, thermophilic temperature is good for hydrolysis and acetogenesis. Mesophilic temperature is good for methanogenesis. So thermophilic process is harder to control, more energy to maintain constant temperature. So co-digestion process with high concentration of ammonia is unstable in the thermophilic temperature. So we need to do two batch reactors. One is for thermophilic, one is for mesophilic. And the pH of around 6.8 to 7.2, the same neutral temperature pH is required to be maintained for higher methane production. Avoid extreme acidification condition. Then the C-band ratio will be again maintained at 20 to 30 in co-digestion process. If the C-band ratio is higher, buffer capacity become poor because more volatile fatty acid will be produced. The C-band ratio is lower, ammonia will be increased. Again inhibit the microbial growth. So here you can see what are the things will have lower C-band ratio. Lower C-band ratio means higher nitrogen value, like food waste, kitchen waste. Higher C-band ratio will have high carbon content, like rice straw, wheat straw. So if you mix food waste and rice straw, or food waste with sugarcane bagasse, so this will give you a proper optimal C-band ratio of around 20 to 30. So here you can see C-band ratio of 400 to 500, C-band ratio of 12 to 35 will be mixed into the mixer. Then we are feeding into the anaerobic digestion process. Then the types of biogas digester. So as we mentioned, the anaerobic digestion will happen inside the digester. So how to design the biogas digester? So digester is a closed container which will produce a methane-rich biogas under anaerobic condition. So under anaerobic condition in the sense, so under anaerobic condition, it should not have any contact with the environmental oxygen. So it need to be a closed container. Then the biogas production will also be further used for cooking and electricity production. So fully stabilized digester sorry, fully stabilized digester slurry, that is called digestate. The final solid product what we are getting is used for fertilizer or soil conditioner, and the gas is used for electricity. Then the three main types of digester design. In the design we have three design types. One is fixed dome type, second one is floating drum type, that third one is back type. These three you have already seen in your school books also: fixed dome, floating drum, and back type. If you are in an institute, you can also see this type of anaerobic digester. I have studied in Anna University. I had seen a floating drum type anaerobic digester for our mess food waste. Whatever the mess food waste we are having, that will be fed into the anaerobic digester with the floating drum type. And many African countries are following this type of back type. I will explain in the upcoming slides. So this we can see the three types of digesters design. Okay. And again it will be divided into continuous mode and batch mode based on the feed. If you are feeding continuously, that is called continuous mode. If you are feeding one time and producing methane, then again we are feeding producing methane, that is called batch mode. Okay, so this is called a fixed dome type. Whenever the airtight container, the dome is the upper circular part, spherical part. When it is fixed in the reactor, then it is called a fixed dome type. Okay, in China it was first initiated. That is called originated in Jiangsu, Jiangsu in China in 1936 itself. It was started. But in India, we have first fixed dome type, that is the Janta model. Janta model. This is the first biogas digester plant in India, but it became unsuccessful because of the construction problem. Then we got Deenbandhu model. So these two model we are going to discuss in the upcoming slides. So please be remember the Janta model is the first fixed dome type in India that was become unsuccessful, and then we got a new design, that is Deenbandhu model. Okay, because the problem what we are having is leakage, cracks in the Janta model. Then we went to Deenbandhu model. Okay, here you can see the Janta model, which is and here it is the Deenbandhu model. If any crack or leakage happening in the main digester, we can get into this secondary chamber and we can seal this cracks. But in the Janta model, it is not able to maintain properly. The digester cannot be maintained. So frequent maintenance cannot be done in Janta model. So it's become obsolete. So advantage of Deenbandhu is good insulation and improved stability, more crack proof, and lesser quantity of building material because it's underground, fully underground. So whenever the construction is underground, we need less quantity of building material. Okay. So the digester will the mixing tank is here. We need to give all the solid waste here. So like cow dung or any cattle waste will be fed into this. So it will go into the digester. It will mix the whole waste, and then the waste will be the outlet gate. Gas will be collected here. Then the digestate will be taken from here. So you can see fixed dome type and fixed dome type in India and fixed dome type in African countries. So the advantages: lower initial cost, longer life, low construction cost, and like less space. But the disadvantages is mesenteric gas holder requires special sealant because it will break any time. This type of sealant, and then high technical skill persons are required for gas leakage systems, and then fluctuating gas pressure will happen, and then excavation, because it is underground, we need to excavate a lot. This much excavation is required. So excavation can be difficult and expensive in bedrocks. Then comes the floating drum type. Why we need to fix the drum? The drum can be floating. Whenever the gas is produced, the drum will come up. Then the gas is extracted, the drum will go down. So the drum will be floating in inside the digestate, or we can have a special water jacket so that the drum can be floating in the water jacket. So this is a good model that is in India. Jamshedbhai J. Patel from India in 1956 first designed the floating drum biogas plant. So that is called the Gobar biogas plant. Gobar is the gas plant which will be majorly used for cow dung as a substrate for anaerobic digester. The floating drum type consists of underground digester and a cylindrical dome shaped with a moving gas holder. This gas holder will be moving, and then directly on a fermented slurry with the this can be directly floating on the digestate or floating on the water jacket. Okay, so the gas is collected in the gas drum which rises. So gases, the drum may rise or move down. So also having a guiding frame. This is the guiding frame, central guide, which will be connected to the partition wall. Okay. So when the feed is coming here, the wall will maintain thermophilic temperature here and the mesophilic temperature here. After the hydrolysis, the last two stages of acetogenesis and methanogenesis will happen in the second reactor. Okay. Then the biogas producer will move the drum up, which will be consumed. Another one model is called the KVIC model, that is Khadi and Village Industry Commission model in Bombay. So it is having improved number of improvement in the design may happen, like this type of partition and a different baffle wall, different types of mixing made the design different. So it has a central baffle and the inlet and the outlet pipe compared to the normal Gobar gas plant. So here you can see some of the digester. This is the rice. You can see the rice. So whenever the biogas is taken out, the drum will go into the digestate. Okay. Easy operation, constant gas pressure, stored gas volume can be seen by the portion. So here you can easily calculate it. So this much high price means how much gas calculated. But in the fixed dome type, we can't calculate how much biogas is produced. But in the floating dome type, drum type, we can easily calculate how much gas is produced. But the disadvantage is steel drum is relatively expensive. In a fixed dome type, we need to use only concrete. But here you can use any type. Steel we can use, plastic we can use, anything we can use for the drum because it will float. But the steel drum is relatively expensive. Painting required to prevent rusting, and the lifespan of the drum is also very short. And then whenever the scum is there, scum is the oil layer at the top, it will struck the gas holder to float. That is another problem. Then the third type is called a balloon type. So balloon type is the one which will be covered the normal reactor only, concrete reactor, digested with the balloon at the dome. So whenever the gas is produced, it will expand. Whenever the gas is not there, it will not bulge. So the PVC, that is a polyvinyl chloride material, or red mud plastic can be used as a balloon for collecting the gases. So pressure in the bag is kept below 40 centimeter of water pressure. Gas produced is stored in the bag under flexible membrane. So it is easily installed in shallow trench. No need of excavation. Can be easily installed in the shallow trench, and it is lightweight. You can see this type of two type two uh, two type reactor also there. One with concrete, one with the balloon. That is semi-bag type. So you can see here, the top one is balloon, the bottom one is concrete. So whatever the gas collected was carried in the bag, it can be easily used in the home for cooking, used as a fuel. So this is called a 4 kg pillows for carrying the biogas. In Kenya and African countries, these people are relying on cattle excreta as a substrate for the biogas production. They will feed the substrate into these tanks, and then it will be reacted in the anaerobic digester at the underground. Then the biogas will be collected in the balloon. The balloon can be carried to their homes, or continuously gas will be supplied. So here you can see the balloons are stored in a column, and the balloons are usually 4 kg pillow can be provided for can provide 4 hours of continuous operation of gas burner. So for easily you can cook 2-3 days with this 4 kg pillows. So again a balloon type reactors. So as I mentioned on single stage and the multi-stage. Single stage is the tank with the one single stage reactors are there with one tank, and the multi-stage reactors are with the two tanks. First is for hydrolysis, second is for methanogenesis. So maintain two different temperatures. Again the design consideration. Sorry. So the digester design is based on raw material availability. So the gas production is directly proportional to how much raw material we are feeding and the type of material. The raw material may be having high CA/N ratio or low CA/N ratio, and then the size of the material. As I mentioned, pre-treatment. So the lower the size, the lower surface area available for the reaction, higher methane production. So the size of the raw material will also play a major role in the digester design. And the heating requirement. In colder areas, we need to do sufficient heating arrangement. Otherwise, this methanogenesis or hydrolysis won't happen. And then burying the digester under the ground will help to maintain temperature fluctuation, because underground there is no much variation in the temperature like ambient temperature. So we can easily bury the digester underground so that the temperature fluctuation can be controlled. Then mixing requirement. Whenever we are having two different feed like co-digestion, we need to mix. So the mixing mechanism need to be designed, and the proper slurry flow need to be maintained. And some production will also be minimized. And then construction material. What are the material we can use to construct the dome, like a steel or a bag or a plastic drum or a fixed dome type with masonry, concrete masonry. These are all we need to fix. But use of locally available expertise and material is cost effective. And then corrosion resistant material. So material in the sense feed material, also the construction material. Feed material like if cow dung is available, we can use some rice straw to maintain the carbon and nitrogen ratio. And then corrosion resistant materials and the larger digester require proper maintenance. Removal of inerts time to time will extend the life, digester life. Okay, these are some of the successful trials in the IIT Guwahati Waste Management Research Group, how they did in different substrate like food waste and different waste, terrestrial weeds, and they also done from different cattle, from smaller cattle to the larger things, how the substrate variation affects the biogas production. So they come up with a different digester design, that is the anaerobic biphased baffle reactor. So in the biphased baffle reactor, they are having different baffle. Baffles are the like paddles, you know. These are the different rods used for mixing the feed. So that increases the biogas production. So here they are having different rods. So they have different advantages like increasing the efficiency and lower concentration of VFA accumulation, and number of baffle provided increasing traveling length. Again, which lesser HRT itself, it will have a good reaction time, and then enhances the attached growth process. So here you can see some of the 1 meter cube floating drum type ABBR. So they are fixing the ABBR. ABBR is their model, that is anaerobic biphase baffle reactor. In Indian scenario, we are using different manures like animal manure, agricultural residue, industrial byproduct, and municipal solid waste, and kitchen waste as a substrate. In household, we can use 1 to 25 meter cube per day capacity of biogas digesters, anaerobic digester. Like fixed dome is Deen Bandhu model and floating type is KVIC model. If it is a community level, as a community, we can do 22,000 meter cube per day of capacity of digesters. So KVIC model, BARC, Nisarguna having a different model, and decentralized containerized solution. And in the industrial scale, they are having more than 2,500 meter cube per day capacity of digesters. So like CSTR, completely mixed distilled tank reactor, and then UASB, upflow anaerobic digester sludge blanket. So you can also read about this type of digester for wastewater treatment. The same can be followed in solid waste management also. So these are the different commercial digesters. Different companies like Biotech, Fluxy Balloons, Aarti Biogas, Fort, and the Biogreens are the Syntax also. We can Syntax is a company that are producing Syntax tanks bioreactors like anaerobic digesters. to produce biogas, which is having HRT of around 25 to 30 days. So major biogas plants in India, Lucknow we are having a plant, Chennai vegetable waste plant. In Chennai you can see in Coimbatore fruit market, you can see a bigger anaerobic digester for vegetable waste market vegetable waste. Coimbatore market, it is the biggest market that are selling vegetables and fruits. Whatever the vegetable and the fruit waste we are getting every day, that is digested in the anaerobic digester. And Vijayawada vegetable waste, and then Ludhiana we are having a plant. Then how much energy is produced from this biogas plants? So every year we are getting increased number of biogas plant in uh, in India. So the installed electrical capacity in megawatts is also getting increased. And then off grid, this is a grid connected biogas plant. This is off grid electrical generation that can be used to transport electricity, and it can be used for this. So what are the policies related to this type of biogas production? Biogas production is again a waste to energy production only. So not only incineration is a waste to energy, biogas production anaerobic digestion is also a waste to energy technology only. So in 1981, first national program of biogas development happened. A capital subsidy was given to the farmers or agricultural people, like as a subsidy for design and construction of the digesters. So if they are having ownership of 2 to 3 cattle, is a criteria for eligible for getting the subsidies. So in 1995, the national program to recover energy from the municipal solid waste was launched. In 2006, the national biogas and manure management program, and then Ministry of New and Renewable Energy, retaining the same objective of producing biogas and can be transported off grid biogas power generation programs, and promote decentralized power options. And then financial incentives were given to the public and private players, and production of bio CNG using biomethanation technology was also launched. In 2016, after the municipal solid waste management and handling rules was renewed, a tariff policy was given for those who are getting 100% electricity generated from the waste energy plant. There is a tariff free things also given, tax free systems are also introduced in the rule. So, what are the different stakeholders in policy level? Central, state, and the municipal bodies are stakeholders in academic research organization, universities, and training institutes. But in financial level, banks and the subsidy providers, and some other innovative instruments. And the economic level, farmers, company, associations, and standard bodies. As a society, NGO, public, and the social entities are the stakeholders in the biogas production. But what are the challenges and what are the mitigations we can do in biogas production or anaerobic digestion? Like the marketing thing, we can see NIMBY syndrome. NIMBY is not in my backyard. Like composting also the same problem is happened. Anaerobic digester also the same problem is happening. In NIST, as I mentioned, we have a anaerobic digester, but whenever I am crossing, there is a smell coming out of it. So the proper technology need to be maintained to for the proper cleaning, and the proper C-bane ratio need to be maintained to lower the order production. So this is not in my backyard syndrome. Nobody will allow to do composting in their backyard. Nobody will allow the anaerobic digester to be constructed in their backyard. So this awareness should be promoted among the public people, so that this type of scientific methods can be implemented. And then market for the organic manure is missing. Whatever the digestate we are getting, that is a good soil conditioner, but people need to be aware of using this in their agricultural field and nascent market. So FCO guidelines should amend this use of organic manure in the agricultural field. Awareness building collaboration with the academic institute will reduce this type of challenges. And then feedstock security, non-segregated waste supply, availability of skilled manpower, which can be mitigated by resource mapping, pan-India adoption, and the capacity building. So you can see lack of creditability, which can be mitigated by proper loan and incentives, and inclination towards power-based project, lack of standards, and lengthier subsidy sanction, which can be mitigated by performance-based incentives, and a balance between the central and the decentralized technology, and the expedite development will mitigate this type of challenges in regulation, finance, operation, and more. Some case studies in India you can see. in Punjab we are having 1 megawatt biomethanization plant for the cattle manual feed from the local goshalas, and 1,000 metric cube of gas storage tank they are having, 2 into 5,000 metric cube digester volume, and this is the gas storage, and the end usage is the power generation. So this is another plant in Gujarat, the 14,000 meter cube in Vadodara, and then feedstock is animal dung and discarded potatoes and pulp and pressment. Because pulp and pressment, whatever we are getting will be having higher COD, which is not easily biodegradable. That can be mixed with the animal dung, that is co-digestion only again. CSTR, that is a continuous stirred bioreactor. We are having some mixing technology, and the digester volume is 2 into 6,000 meter cube. Again used as a bio-CNG for industrial use. Digestrate is used as a fertilizer and sold in the market. In Maharashtra, we are having a decentralized biogas to power project of 25 kilowatt in Pune. So feedstock is around 5 tons per day. Using vegetable market, hotel and colonies. Two-stage digestion reactor is again having aeration and leachate circulation. So aeration in anaerobic digester is like aeration is only for hydrolysis process, not a proper aeration system. Again, whatever the leachate we are getting, that is recirculated into the system in the anaerobic digester. They are having 275 meter cube reactor, and the digester volume is 200 meter cube. The end usage is the illumination of street lights in and around the Pune area, the reactor areas. So this is all about the anaerobic digestion. So we need a proper collaboration of the local authorities and the academic and research to design to have a proper design of anaerobic digester, so that it will become a successful treatment technology. Okay. So this is all about the anaerobic digester and the type of the stages of anaerobic digestion, factors affecting anaerobic digestion, and design of digester, and what is called co-digestion, and what is the pre-treatment of anaerobic digestion. Okay. If you have any doubt, please unmute and you can ask, or you can post it in the chat box. We can also we are going to discuss about the old problems, old assignment problems. Can I move on to the assignment problem? If you don't have any question, I will move on to the assignment problems. Please post the answers in the chat box. I'll move on to the first question. So this is a multiple choice question. Why is the pre-treatment done for substrate in anaerobic digestion process? Biomass integration, biomass disintegration, improved solubilization, decreased solubilization. So more than one answer may be correct. The answer is why we are doing pre-treatment. We need biomass disintegration, and we need to increase the solubilization. So option B and C are correct. So what is pre-treatment? Whatever the complex organic matter, that should be converted into simpler organic matter in the hydrolysis process. But this is a rate limiting step because it's taking more time. So we need to reduce the HRT by reducing the time taking for the hydrolysis process. For that we need to do pre-treatment. So various pre-treatment options like physical, chemical and biological methods are there, which will disintegrate the biomass, which will improve the solubility of the complex organic matters. Okay. The second question is, what is the percentage composition of hydrogen in biogas? So in anaerobic digester, we are getting biogas as a product. In biogas, we are having major two compounds. One is methane, another one is carbon dioxide, and some trace compounds like hydrogen, nitrogen, and H2S. What is the composition of hydrogen in the biogas? So hydrogen is around 0 to 1%. So you can see here, methane will be 40 to 70%, that is 65. Carbon dioxide is 30 to 60, that is 35. If more than 44% of carbon dioxide is there, no flame will happen. So other gases will be around 1 to 5%, out of which hydrogen is 0 to 1, hydrogen sulfide is 0 to 3. Okay. So please be conscious about this composition of biogas, it is very important. So methane will be higher, 65, carbon dioxide 35, hydrogen 0 to 1, hydrogen sulfide 0 to 3. Again, everything is based on volume basis. Okay. So third question, pre-treatment of sludge. So we are doing pre-treatment of sludge, industrial waste,
So,
all
so what is the what
uh,
is the answer for question 2, sir?
0 to 1%, ma'am.
Okay, okay, okay.
Uh, 0 to 1% is high. So the third question is pre-treatment of sludge during the anaerobic digestion process is done to, this is again a multiple choice question. Increased retention time, lower biogas yield, improved biodegradability, increased biogas yield. You can post the answer in the chat box also. So to increase the biogas yield only, we are doing pre-treatment. So option D is correct. Option B is wrong. And increase the retention time, it's wrong. So reduce the retention time only because to remit the late remitting step is the hydrolysis process. So it will take more retention time. So reduce the retention time only, we are doing pre-treatment. So option A is wrong. Option B is also wrong. And improved biodegradability is correct. Improved biogas yield is correct. C and D are correct. That is the pre-treatment for sludge biomass. So what are the extracellular biomass will be disintegrated. So it will improve the biodegradability and it will lower the retention time and higher biogas yield. That is the ultimate aim of pre-treatment. So the sequence of anaerobic digestion process. So we have 4 stages of anaerobic digestion. What is the sequence? The first, the complex organic matter is converted into simpler organic matter. The simpler organic matter will be converted into volatile fatty acids, and the volatile fatty acids will be converted into acetic acids, and the acetic acid is converted into methane. So what is the process now? So option is C: hydrolysis, acetogenesis, and methanogenesis. Okay. Complex into simpler organic compound. Then the simpler organic compound will be converted into volatile fatty acids by acidogenesis, and then the volatile fatty acids are converted into acetic acid, that is called acetogenesis. And from the acetic acid or from the H2 plus CO2, methane will be formed, that is called methanogenesis. Okay. The answer is C. The fifth question: the optimum range of pH during methanogenesis. Optimum range of pH during methanogenesis. So in hydrolysis and acidogenesis phase, acid will be formed, volatile fatty acid will be formed, which will reduce the pH to around 4. After that, due to buffering capacity, it will be again increasing, and the optimum pH required for the methanogenesis is around neutral. 6.5 to 7.5 is the neutral pH required for methanogenesis. So if the pH is lower, then methane inhibitors inhibiting the growth of methanogen, so no more methane will be produced. And if the pH is greater than 8, toxic substance will be produced. Again, it will reduce the methane production. So we need an optimum pH range of around 6.5 to 7.5. So answer is 6.5 to 7.5. So the sixth question: what is converted to peptides in the hydrolysis process of anaerobic digestion? So in anaerobic digestion, hydrolysis stage, complex organic matter is converted into simpler organic matter. Complex organic matters are protein, fat, polysaccharides, which will be converted into which is converted into peptides, protein or fat or polysaccharides. So the protein is converted into peptides. So option B is correct. You can see here, protein is converted into that are all insoluble complex organic, which are converted into soluble simple monomers. So proteins are converted into peptides, polysaccharides are converted into fatty acids, and fats are converted into saccharides. Okay. So proteins, which is converted. Question is which is converted into peptides in the hydrolysis process. So answer is protein. Okay. The next question: high level of simple sugar result in high level of simple sugar. Whenever we are having higher simple sugars, which is easily biodegradable, then the acidogenesis phase will be more, then more production of volatile fatty acids. The answer is VFE accumulation will be higher. High level of sugar molecules, high level of VFE accumulation. It's called the factors affecting the anaerobic digestion. Whenever the carbohydrate rich compound, that is the higher sugar level are present, where it is. Higher level of simple sugar result in rapid volatile fatty acid accumulation, which will decrease the pH. So we need to add some non-readily biodegradable organic matter with the readily biodegradable organic matter. That is the balance. So lower content of easily biodegradable material will be added. Then, what is the disadvantage of Deen-Bandhu biogas digester? So we have two systems. One is Janta model and Deen-Bandhu model. Both are fixed dome type. So what are the disadvantages of Deen-Bandhu biogas model? Why we went to floating type? Now everywhere floating type is followed. Because in Deen-Bandhu biogas digester, okay, this is a tricky question. They are comparing the Janta model and Deen-Bandhu model. The Janta model having more leakage, decreased stability, and higher reckoning cost. Deen-Bandhu model having no disadvantages like this. But the process is we don't know how much biogas is there, and we are having more construction cost. That's why we went to floating type. Okay. So here you can see Janta model having this type of disadvantage. That's why we went to Deen-Bandhu having this other advantage: good insulation, improved stability, more crack proof, lesser quantity of building material. Floating drum plant consists of floating drum plants consist of moving gas holder, floating drumlet, moving gas holder, static gas holder, guiding frame, none of this. So in floating drum biogas plant digester, we have three modules. One is a fixed digester and a moving gas holder and a guiding frame. So option A and C are correct. Say fixed digester will be there, underground digester which is fixed, and then a moving gas holder is there, and then a guiding rod, central guiding frame is there. So this is the three component of floating drum type digester. Then the question: what percentage of methane formation is from acetic acid? From acetic acid itself. So we have different type of acid from the acidogenesis phase. All the simple compounds are converted into acids, but majority are acetic acid. Some part of butyric acid, like some of these are so almost 70 percentage of methane will be produced from acetic acid itself. I'll show you the slide again. So other 30% are from some other acids like butyric acid and lycric acids and all. Okay. But acetic acid itself will produce 70 percentage of the methane. Then COD reduction in conventional anaerobic sludge treatment. What is the COD reduction in the conventional anaerobic sludge treatment? So it's around 30 to 35% COD reduction in the conventional anaerobic digester. But if we are adding co-digestion process or a pre-treatment method, it will increase the COD digestion. That's why we are doing pre-treatment. Okay, and the COD balance is about 90% will be converted into biogas and 10% will be coming into the digest rate. Again, the same question: which is converted into peptides? So protein is converted into peptides in the hydrolysis. Then the pH during acidogenesis phase. pH for the methanogenesis is optimum pH is 6.5 to 7.5. But what is the pH during acidogenesis phase? Which is the acid forming. Volatile fatty acid will be formed. So at the acidic phase, the pH will be around 4. Okay. Then pre-treatment of biomass can, again the same question, improve solubilization, disintegrate biomass, improve gas yield. So all the three are correct. Improve solubilization. So we need a good soluble substrate. We need a good disintegrated biomass, which will again improve the biogas yield. So that's the ultimate aim of pre-treatment. Biomass disintegration, improved stability, biogas yield. optimum pH range of methanogenesis 6.5 to 7.5. Then optimum Sebain ratio for anaerobic digestion. This is another important factor. Sebain ratio. So for composting also the same 20 to 30, here 20 to 35 for the anaerobic digestion process. If the C is higher, we need to volatile fatty acid production will be more, so we need to add a proper some other substrate as a co-digestion. If the Sebain ratio is very low, then ammonia will be produced from the nitrogen, which is again a inhibitor for methane microbial population. So a proper optimal Sebain ratio of 20 to 35 is required. Then the sequence of anaerobic digestion, hydrolysis, acetogenesis, acetomethanol. C is correct. Then the disadvantage, this is the important question. What are the disadvantages of thermophilic temperature range during anaerobic digestion? So we need to maintain thermophilic temperature because we get a good hydrolysis process. But at the same time, we have disadvantage also because it will inhibit the methanogenesis phase. So increase the free ammonia content. So that is the problem with the thermophilic phase. So whenever the thermophilic temperature is higher, it will be hydrolysis will be good. Increase the rate kinetic, it will reduce the HRT. That is not a good process. But negative effects are ammonia will be inhibited. Hello. Am I audible now? Sorry for the technical glitch. Okay. So here some of the negative impacts are ammonia inhibition. For that we need to use mesophilic temperature. That's why we are considering two different reactors, one with the thermophilic, one with the mesophilic temperature for first two stages and the second two stages. So that's all about the assignment problem solving session. So if you have any doubt, please unmute and ask, or you can leave the meet if you don't have any question. Also, you can post it in the chat box. Thank you so much for joining. That's it about today's session. I'll close the meet because of some network issue. I'll close the meet. Thank you so much.